morning again. Everything is fine. Okay, I posted on IOL survey of your opinion on me, so please complete it. Okay, it's anonymous. Not now, not necessarily now, but you can do it now, no problem, but, because it's very quick, but not necessarily now. It's anonymous, and it's just a way for me to get some input from you in order to steer my next lectures. And I really appreciate if you give me your feedback. Okay, and don't forget, I saw that some of you already completed the self-assessment test. Don't forget to do it. And if you have any question on it, that's fine. We can also, if you want, later on, we can discuss the questions and see what my reply would be to them. Okay. Now, today I asked you if you could bring your PC, because I would like to make an exercise. And if you don't have enough computers, I would suggest that you group in small groups. But if you have it, I would prefer if you take yours, of course. And today I would like to move forward with an exercise. It will be a little bit complicated. It's a big step forward in R, what we are doing today. I need to make with the exercise, I need to make significant step forward, significant steps, meaning that I cannot really go step by step because we cannot dedicate to exercises many hours. I told you that at the end of the story we will dedicate like 8 hours to exercises, and then I need to go a bit quick with them. I think you have all the meanings and skills to stay online with me with these big steps, but of course you need to make some homework. I just would like, before I start, to remind you that next week there are no lectures, so we'll meet again on Monday, April 15, I think, and then there is the Easter break, so another long break up to May, I think. And then at the beginning of May we can discuss again about the calendar, etc. And remember that we didn't fix any date for the exam, I just gave an indication, okay? So if we stick with this calendar, I told you that probably we will have the first exam June 10, 11, as soon as we can with the official date. So please look at the completion date of the subject, and next Monday we will make the first exam. But beginning of May, I would like to discuss with you again if you would like to anticipate it. To anticipate means that we need to recover some hours. Don't forget that May 16 there is our field trip. It's half a day. I distribute through IOL subscription list. I'd ask you to subscribe on IOL. Okay? I send you an email with IOL. I think you are all subscribed because I see there is a long list of subscribed people. Okay, that's all. Now the exercise. If you look at the web page of the course on my website, keep in mind exercises are not in IOL, not yet. Maybe that I decide to post them there, but not yet there. And if you look at the exercises, you see two more with respect to last time. There is an application of the linear reservoir rain for runoff model. For this exercise, there are the data, there is the text, but there is no example R file. I didn't provide any example because this exercise was meant as a, a self-made exercise without any additional input in the form of list of R instructions, because this is something that is just for you. My suggestion is let's skip it now, let's pass to the next one, and my suggestion for you is don't forget to make also the linear reservoir, because it's much easier than applying iMode. Even applying iMode is not so difficult, but linear reservoir is much easier, and once you completed iMode in a good way, I explained to you what a good way in my intention is, you'll be able to do the linear reservoir exercise by yourself. So iMode, you see that there is a link with the text of the exercise. We will open it together now. there is a link with suggested R code, and there is a link to rainfall and evapotranspiration data and river flow data. So let's explore these links one by one, okay? So first of all, let's look at the text of the exercise, and I think it's better if I turn off the slide just 1 second, because otherwise it's a bit tricky to read on this screen. Oh, it's not so bad, but let me do this. Okay, so you see we need to apply IMOD. So you see there calibration and validation. These are two terms that you still don't know. Let me just say that calibration is parameter tuning. Okay, I told you that it's a bit of a problem to make it trial and error, but we will start with the trial and error. Validation is something that you still don't know. Don't forget about it for now. So in a river cross-section, draining a catchment whose area is 1,200 square kilometers plus 14. River flow data have been observed at hourly time step for a period of 1 year. At the same time, precipitation and potential evapotranspiration have been estimated. Okay. The related observations can be downloaded at these addresses. Don't copy them because you have the links on the website. By using the above data set, the IMOD model should be calibrated, so parameters should be tuned, by using sum of squares as objective function. I'll explain you what I mean, but I think you already know what is sum of squares, but I'll explain you what I mean. The initial value of the river flow is set to 15, okay, because we need a starting value for the river flow in order to run IMOD. And I'll show you how to set it. Comparison should be made by using the sum of absolute errors as objective function. Let's forget about it for now. Okay, and let's forget about this subsequent line. Also, let's forget about explaining a brief report about elaboration with the required graphs. This is not necessary. You're not required to bring at the exam any report. Okay, so let's forget about it. Okay, so let's see the data first of all. Okay, so rainfall and evapotranspiration. If I click here, I see that there is a file that appears which shows hourly rainfall in the first column. This is rainfall over the catchment. The catchment is considered to be land, remember, with IMOD. And the second column is evapotranspiration. You see that rainfall begins with a sequence of zeros because rainfall is intermittent. It's typically an intermittent data set. They are non-zero only when it rains. So if you scroll down, you will see that there are some value different from zero there. In the right column, evapotranspiration, you see that it's constant, and the reason is that usually evapotranspiration is modeled at monthly time scale. So what we do usually in hydrology is to keep evapotranspiration constant for 1 month. If you scroll down again, you will see that the value changes. Now, the problem is that this is a web page. I need to save the data in a file to be uploaded in R. And this is quite simple to do. You have to right-click and click on Save Page As. And then save it in Documents if you are a Windows user. If you are a Mac user, you should know the path from which R reads. So I save in a different directory because I am a Linux user, but again, you see that there is already the file name that appears. Probably you don't see the extension .txt. Don't put it, okay? Just save the file with the proposed name. You don't need to change anything here, okay? So I am saving. Once it's saved, you can go back and save the second one, namely the river flow data. And these are the river flow data. It's just one column. Again, I right-click, Save Page As, and I save with the proposed name in my directory. Good. So let's go back. Okay, now, are you online with me? Somebody still working? No, it seems not. Let's click on suggested R code. Okay, you see that there are a list of instructions. This is the code for the application of imod. If you forget about the first line, imod function par, I'll explain you later what it means, you see that there are a list of R instructions there. A list of instructions is already a program, okay? And the trick is that we have to understand what each instruction means. The first ones are very simple, like area of the basin in square meters, it's reported there. This is a definition. We define the area of the basin according to the information that the text of the exercise gives us. Good. So these are simple, very simple instructions. But as we go down, the instruction will become a bit more difficult to understand. You see that there are comments. Again, I would like to stress again that when you write a program, you need to make comments. In this file, there are too few of them. Okay, when you write a program, just if you can, try to comment each line. If not each line, try to make more comments than here. Okay, because as I said, it becomes very difficult even after a couple of weeks to remember what you did, because it's not easy. Because you know it's not a list of instructions is not explained. It's not like writing in Excel where everything is clear. Okay. I said that we need to understand what each instruction does. This is extremely important. We are allowed to use programs, and this is a program that is already available. It's provided in order to make your job easier. You may also find programs on the web. And of course you have to use them. If you find something that is already prepared, like in this case, why not? But it's extremely important that you understand what the program does, because otherwise you cannot check whether it's correct. Because you have to assume that the program can be wrong. In fact, even the program that I'm giving to you today may be wrong. In fact, some years ago, I gave another version of this program, and one student told me, look, here there is a mistake. So, unless you use something that you know for sure that it's already fine for some reason, but this happens quite rarely, but of course, if you use AutoCAD, you don't need to look at the code. You know that it's a program that is commercial, that is well tested, etc. If you use Excel, same thing. In the past, people had fun trying to find bugs in Excel, and they were successful. So even Excel, it's not 100% sure, okay? But if you use a program that you found on the web and it's not very clear if it is much used, widely used, or if you find a program given by the professor and it's not absolutely granted that it's correct, you have to check. And the best way to check is to look at the program and understand what it does. Okay? And this is indeed something that is important, because I already mentioned to you that if you make a mistake because you use a wrong program, you cannot say to the judge that it's the fault of the program. It's your fault, because you are not supposed to use something without understanding, without checking. Okay. Okay, so we can use this, but we need to check. Before I go step by step to look at these instructions, let me now explain to you why I put the first line, imod function par. You know that in R there are functions, and they are embedded in R. And functions have arguments. We know that there is the help to understand what arguments we need to give to each function, what arguments have default values. Okay. Now, the news of today is that we can write functions for R. So we can personalize R by increasing the number of functions. What is the advantage of a function? The advantage of a function is that you can run the function with just one line of instruction. You don't need to cut and paste. In this case, for running imod, you don't need to cut and paste everything. You just need to write in R imod and give the arguments. And this is the way to write a function. You have to define the function through a function that is called function. Okay, so you define imod, which is the name of the function, and I was very creative. I gave it the name of the model. Imod is equal to function, and between parentheses I have to give the arguments. In this case, the argument is just one, par. Par is a vector with parameter values. Remember, we have 5 parameters. Okay? I don't give any default, which means that when I run this function, I need to give this argument. It's possible to give defaults. Let's see it later, or if we don't see it together, just look at on the manual how to give default values. Okay, look here. Here I have a curly bracket. Let me see if I can. Yeah. This is a curly bracket. As usual, we can use curly brackets to group a set of instructions. This opening curly bracket means that what follows up to the closing curly bracket is the list of instructions that compose the function imod. Okay, now let's start with the list of instructions. This one is definition of the area of the catchment. I think there is nothing more to say. The second one is definition of the time step. It's hourly time step. If you look at the text of the exercise, we need to run the model at hourly time step. Now, we need to make sure that units are coherent. Therefore, given that we have river flow data in cubic meters per second, an idea could be that we define everything in meters for the length and second for time. So this is why the area of the catchment is expressed not in square kilometers but in square meters, and this is why the time step is expressed not in hours but in seconds. This instruction defines the number of time steps. The exercise is clear. It says that it's 1 year. 1 year is how many hours? 365 times 24, which is 8,760. Here there is written, be careful to adjust as needed. It's a comment. Look at the comment is placed on the same line after the hash sign. Everything is placed in the line. After the hash is ignored by R, is a comment. Adjust it because if you want to run the model for 6 months, then you need to adjust the number of time steps. Okay, then here there is the initial flow. Remember in the exercise we said there was written set the initial flow at time 0 to 15 cubic meters per second, and this is the setting. We will see how to impose to imod this value. Here there is a conversion factor. Let's forget about it for now. It's something that you can easily understand later on. So let's forget about it for now. Okay. I think up to now everything should be clear, but if you have any question, please let's interact. Okay? Now we have the definition of the parameters. The parameters, yeah.
About the n delta t, how we can calculate it?
N delta t, I think you can leave it as it is now. Okay? And we don't need to change it. But I just wanted, because in the exercise, if you read the last line that I said forget about it, it says to change the length of the simulation. Okay, so for now we can forget it. Now, here there is a definition of the parameters. Parameters are contained in the vector par, P-A-R. For the sake of clarity, I prefer to transfer the element of the vectors into variables in order to better recognize what is the meaning of each parameter. So Cmax, we remember what is in IMOD. Let's give to Cmax the first element of the vector par, just to better remember it, okay? Because otherwise I could continue without defining Cmax and using just par 1, but then I run the risk of not remembering in the vector par what is each element corresponding to. Okay, so we have, as you remember, 5 parameters. So I need to define Cmax, beta, alpha, Ks, and Kq. Remember what they are. Cmax, max storage in the catchment. Beta is the exponent of the probability distribution that regulates the soil storage. Alpha is the splitting parameters between low flow and quick flow in propagation. K slow is the parameter of the linear reservoir, the only one that makes the propagation. K quick is the parameter of the 3 linear reservoir for the quick propagation. Everything is hopefully clear. Okay. Now we initialize the variables. Remember that in in IMOD, we have 2 key variables that are W and C, varying in time. C is, remember how we defined it, is water storage in the areas of the catchment that are not saturated. This is C. W is the storage in the catchment, including saturated and non-saturated areas. W is lower than C by definition. Okay. These values, W and C, need to be computed at each time step, because they are WT and CT, so they are varying with time. Each time step I need to compute them. But if you remember, given that we are working with a finite time step, we need to compute W and C at the beginning, at the end of the time step. So at each time step, we need to compute C and W twice. Why twice? I just remind you. Because at the beginning of the time step, we get rainfall, if there is rainfall, and then we update C and W. At the end of the time step, we subtract evapotranspiration, and we have to recompute C and W. Okay, so this is why, when I'm defining these variables, C and W, I am defining them with C1 and W2, because I need a C1 and a C2, and I need a W1 and a W2, beginning and end of the time step. So for now I'm defining these two, W2 and C1. Okay. Now, what follows is the definition of the water content of the linear reservoirs. Let me go back to my web pages and get the scheme of IMOD. Just 1 second, because I think it is useful if we refresh it. Just 1 second. Okay, here it is. Here is the scheme. Okay, so remember that for propagation we have 5 linear reservoirs. Okay. Keep in mind that we have rainfall entering into the catchment in millimeters per hour. Okay, our rainfall data are millimeters per hour. And given that we need to compute C and W in these are storages are expressed in length. Keep in mind that when we add rainfall over the catchment and when we add the input into the reservoir, we have to decide whether we want, I express storage, C and W, and the content of the reservoir, the volume in the reservoir, in millimeters or meters. This is why there is a conversion factor that was introduced at the beginning. Okay? I anticipate that we will express them in millimeters, and therefore we need a conversion factor. We need to convert the units. Now, the instruction that I was explaining to you, the next one, defines the initial content of these reservoirs. Why do we need to define an initial content? You may say, let's set it to 0, because why we need to set an initial content there? Indeed, we can decide to set some of them to 0, but if we want to get a Q0 equal to 15 cubic meters per second, we have to put some water, at least in one. And we decide to put water here. So we give a water content to this reservoir below, such that at time 0, even with no rainfall, I have a QT here that is 15. So the next line of the program serves to this purpose. Okay, let's see. Look, W's law. What is W's law? W's law is the water content in millimeters in that reservoir. And in order to compute it, we want to fix a W's law such that we get Qi river flow at time 0. Remember Qi, if you scroll up, it's 15. It was defined equal to 15. Okay, so this is the way to give W's law such that if you compute Qi subsequently as W's law divided by K, you get such number. Okay? There is the conversion factor. So you see here that there is indeed Qi divided by K's law, it's equal to W's law. When you compute Qi at the first time step of IMOD, what do? You get W's law divided by Qi and K's law, and then you get precisely Qi. Okay? Remember one thing, that here, for some reason that are related to the original form of the program, which I didn't change, K, the parameter K of the linear reservoir, is expressed in 1 over time. And I need to explain a little bit what I mean. if you remember when we introduced the linear reservoir, we defined it in this way. There is an input and there is a bottom discharge, Q. You have a water content W, and here you have Q, and we said Q is equal to W divided by K. This is what we said. And said the unit of K is time. In this case, this program uses adopt as K, 1 over K. So in I mode, what they did is to define Q as W times K. So they took the inverse of the value. I didn't change it. I don't think it is reasonable. I didn't change it for one precise reason. You can find other codes for iMode on the web, and even for R. And therefore I wanted to conform to what you find on the web. But, you know, I don't think it was a good choice, because we are used with the linear reservoir to think that, to assume that K is a dimension of our time. Here, K as the dimension of 1 over time. Is this clear to you? I needed to say this because you see here that it's coherent with this last assumption, not with the previous one. Because W cannot be seen as a river flow divided by time. It's a river flow multiplied by time. Okay? It's just a matter of convention. That's it. And then there is the conversion factor. The conversion factor, you need it because I want to give W in millimeters. Okay. I'm not sure that W is in millimeter actually. Let's see what is the conversion factor. I am sure that Qi is cubic meter per second. Divided by, multiplied by time is cubic meters. So let's see W's law, what is, okay? And let's see the conversion factor. Okay, the conversion factor is 1 divided by 1000. And this allows us to pass from meters to millimeters. It's divided by the time, let's look first of all, multiplied by the area of the basin, which means that W is in cubic millimeters. Area of the basin is in square meters, so it's W is probably expressed in just 1 second, because I don't remember this step here. So it's K's law, it's expressed in second. Okay, so let me see. Because there is the time step is the number of seconds in the hour. So it's just a matter to understand what is the unit of K's law. Just 1 second. And time step, okay, so K's law is in hour. This is fine. And then the area of the basin is in millimeters, but you know, this instruction here is not really important. It's not really important. It's not really important what is the conversion factor here, because then what is computed here, W's law, is used back to compute Qi, and therefore whatever the value of the conversion factor that you put here, at the end of the story you get back again Qi. The problem is that if we want to determine what is the unit of W's law, then the conversion factor matters. I want to explain better because I don't think I was clear up to now. Whatever value you put here in the conversion factor, it is effective on the value of W's law, okay, for sure, because you start from a parameter, whatever its value is, but what you put here affects W's law. Then W's law is not used, is not given back by the model, it's just used to compute back Qi at the closure of the catchment. So it's not really effective, the value of the conversion factor on Qi, because the value of W's law is then divided again for K's law and conversion factor later. It is effective on W's law. So my question now was to understand what is the unit of W's law that we obtain. This unit, I don't think it is correctly computed with the conversion factor in this form. Okay, I'm saying that because it is divided, it is obtained the conversion factor by dividing by 1000. And dividing by 1000 is needed in order to transform from meters to millimeters. But then it is multiplied by the area of the catchment, the conversion factor here, which is again in meters. So if I use the conversion factor in there, I don't get a coherent unit for W's law. But we can ignore it for now. But I just wanted to point out that this is a bit inconsistent. So this is a mistake in the program, which is not affecting in the final result, but it's only effective on the value of W's law, on the unit of W's law, which is wrong. Okay, I realize it now. And this is why I tell you, you should try to understand everything. I realize that you may not be convinced that it's not